All right, ladies and gentlemen, welcome to AP Statistics at Irvine High. My name's Rich Crow, and I will be your teacher this year. Apologize that we can't meet in person on day one, but it is what it is. So today, I just wanted to cover, we have a course contract, find it on Canvas, get it signed, send it to me. You'll see there's also an assignment sheet on Canvas that'll tell you what your homework is. You will be given a formula sheet for this class. It's the same formula sheet that you will get when you take the AP test. And I do have extra credit passes. I call them absolute absolutions. We'll get into that in more detail when we actually meet live in person. Okay, so here we go. Our first lesson. Lesson 1.1. The way I'm going to work the distance learning is I'm going to make videos like this. I'm going to ask you to watch the videos as your homework. And then during class time, we'll go over the homework problems, the problem set together. So that'll be kind of our live instruction. I'll answer questions about the video that you watched, and I'll go through the homework problems with you. So basically doing what they call flip teaching, at least in the beginning, and we'll see how it works. So lesson 1.1, topic here, displaying data graphically, which is one of the main things we do in statistics. So I'm going to go over a ton of different graphs today, and most of them you probably are familiar with. And that's going to kind of be the way the course works. You're going to be familiar with almost everything, at least in the beginning. But we're going to expect you to be able to interpret these things. And that'll kind of be the new piece of the puzzle, the interpretation, not necessarily just making a graph or calculating a mean. All right, so the overall objective of statistics is simply to analyze data. And then, of course, there's a lot of ways that we analyze data. Okay, so we can interpret the data graphically, we can interpret the data with calculations, and then of course we use more advanced methods when we perform inference. And that's really where AP statistics takes off, is when we do inference. And that's most of second semester, inference. Most of first semester we'll be living up here, learning different calculations, learning different graphs, and then second semester we'll kind of put it all together and do inference. All right, so day one, we're doing a variety of graphs, so we need some data. So an example that I came up with, that I think is interesting at least, is the computer keyboard. I don't know how familiar you are with the computer keyboard, but there it is, right? That's the keyboard you're familiar with. Okay, now a little background. How did we end up with our keys organized in that way? Usually somebody in the class knows, but obviously since nobody's in front of me, I can't let you answer, so I'll have to give you the answer. Long ago, when the first typewriters were being made, the keys were not lined up in that kind of haphazard way. The keys were alphabetical, and people were actually finding the keys too quickly, and they were jamming those primitive typewriters up. So somebody had the bright idea, let's scramble the keys and mix them all around to slow down typing. And it turns out we still have that same layout on our keyboard, a scrambled up design that was purposefully created to slow down typing. Even though technology has improved greatly since those early typewriters, and in theory, we could lay out the keys in any order we wanted, including an order that would be beneficial to speed up our typing. So the traditional keyboard, we call it the QWERTY keyboard. That's the one with the scrambled up letters with the goal of slowing people down. And then there's a new keyboard called the Dvorak keyboard. And the goal of this keyboard was to organize the keys in a way that would actually speed up our typing. Now, the people that created this Dvorak keyboard, obviously their goal was to make a better keyboard and to sell it to the world. But as you may have noticed, I don't think any of you have that keyboard on your laptops or your phones or anywhere else that you type. So it looks like it didn't quite work out. But let's go over the logic of this keyboard and talk about what they did. So we needed to, or they needed, the creators of the Dvorak keyboard needed a way to compare their keyboard to the QWERTY keyboard. Now, on the surface, the easiest thing to do would be ask someone to type a paragraph on the QWERTY keyboard, type the same paragraph on the Dvorak keyboard, time them, see what's faster. Hopefully, everyone sees why there's a problem with that method. Familiarity with the existing QWERTY keyboard, right? That's going to bias our data set. So an alternative idea might be find people who have never typed in their lives and have them type 2 paragraphs, 1 on each keyboard, compare the times. But that data is not very good because if someone's never typed in their life, well, then they're hunting and pecking on both keyboards, and they're both going to be basically really slow times, and you're not going to notice much of a difference. So the idea here is somebody who knows how to type, knows how to use the home row. On the Dvorak keyboard, more of the frequent letters are found on that middle row, the home row. That's the way they designed it. So in order to collect data in an objective manner, they came up with a scoring system. And they said letters on the home row or middle row will get a score of 0. Letters on the top row, score of 1. Letters on the bottom row get a score of 2. This is not necessarily the best scoring system in the world, right? They're saying I could type 2 letters on the first row in the same amount of time I could type 1 letter on the third row, and so on and so forth. So the proportionality of this scoring system is questionable at best, but we can at least agree it's an objective scoring system. So whether or not it's highly accurate, we can debate. So let's go with their scoring system just because that's what they actually did. All right, so here is the QWERTY keyboard up here. Let's practice. We're going to take the word easy. We're going to score it on the QWERTY keyboard. So easy on the QWERTY keyboard. I find E right here. That would be 1 point on that row. Then I find A, home row, 0 points. Then I find S right there, home row, 0 points. And then I find Y right up there, 1 point. So on the QWERTY keyboard, it's 1 plus 0 plus 0 plus 1, or in other words, a total score of 2. Doing the same thing down here on the Dvorak keyboard. I find E on the home row, that would be 0. A on the home row, 0. S on the home row, again, 0. And then Y is up here on top row. So on the Dvorak keyboard, the word easy would get a score of 1. Okay, now notice, that's only one word. Just because I have a higher score on the QWERTY for that one word doesn't automatically make Dvorak better, right? I'm sure we could find words that have a higher score on the Dvorak keyboard than on the QWERTY keyboard. And of course, one word is not a data set, right? Statistics, we analyze data sets, not a single number. So what we need to do is we need to take a sample of words and score them on both keyboards so we could compare. So the sample of words we're going to take are the 52 words contained in the preamble of the Constitution. So go ahead and repeat that with me. 407 years. No, that is Gettysburg Address. Preamble of the Constitution. We the people of the United States in order to blah, 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 blah. Okay, so there's our preamble. There's our QWERTY keyboard. We're going to score all 52 of those words on the QWERTY keyboard, and then score all 52 of those words on the Dvorak keyboard, and then compare. And the theory is, if I have lower scores on one of these two keyboards, that I have more letters occurring on the home row and the top row and much fewer on the bottom row, and therefore I should be able to type faster on that keyboard. Now, feel free to score all these words yourself if you really want, but I've done it for you to save time, so oops, here we go. So here are the scores for all 52 words in the order they appeared in the preamble of the Constitution, scored on the QWERTY keyboard. And this is the case with data sets, right? You get a set of numbers and it's just a set of numbers. So the first thing you need to do when you are presented with a data set like this is put the data in ascending or descending order. We normally put it in ascending order. So that's what I would do next. So here we go. Here are those 52 words scored on the QWERTY keyboard, but instead of being in the order they occurred in the preamble, they are now in ascending order by score. So you can see the word A scored 0 on the QWERTY keyboard, and over here, I can't remember what word it was, but our highest scoring word scored 14. Okay, now that my data is in numerical order, ascending in this case, I need to make a table. Once I have my table, that's when I will get into making graphs of my data. Okay, so let's talk about how to make a table. When you make a table, you need to organize your data into what we call classes. Okay, a class is simply a range of values. So I could, for example, with grades, I could say, oh, 90 to 100 is an A, right? 80 to 90 is a B, so on and so forth. That would be a class. It's a set of values that I group together. So I need to put my data into classes. Now it's very important that my classes are disjoint, or in other words, mutually exclusive. I can't have one piece of data landing in multiple classes because then I would be double counting that piece of data, right? So each class has to be disjoint, no overlap. When I set up my classes, I need to make sure that they cover all of the data in the data set. I can't just cut it off because I feel like it or because it's easier. Now we would like to have our classes be the same width or the same size. So with, again, grades, you might say, 0 to 9, 10 to whatever, and so on, 80 to 89.9, whatever. And lastly, we don't want to have too many classes. We also don't want to have too few classes, right? I could say, oh, my class is negative infinity to positive infinity. Well, then my graph will simply be one bar, right? And it'll just tell me how many pieces of data I have. It won't show me the distribution of said data. So we want to make classes that cover the whole data set with the same size, and we want to create 5 to 20 classes. Now, how do I know? Should I shoot for 5? Should I shoot for 10, 15, 20? Well, this depends on how much data you have. If you have a very large data set, having more classes is just fine. But if you have a small data set, for example, let's say I only have 20 pieces of data, don't really want to make 20 classes because I'm probably going to have a lot of classes with only 1 or 0 pieces of data, and I'm not really going to get a graph that shows the distribution very well. So the smaller the data set, the smaller number of classes I probably want. Larger data sets, larger number of classes makes sense. But there is no one right answer. Okay. All right, so next, important vocabulary term, frequency. That is how many pieces of data do you have in your data set that land in a class. Okay. Now notice, this is just an aside, it's common sense. The sum of the frequencies will equal the number of pieces of data in your data set. So when you're done making your table, at the end, add up all your frequencies and make sure it matches the number of pieces of data. So in our example, we have 52 words. So when I'm done making my table, I better have 52 as the sum of my frequency column. Okay. Now, aside from a straight frequency table, we also will sometimes create relative frequency tables. A relative frequency is simply the actual frequency divided by the number of values in your data set. So, in other words, oftentimes these are given as percentages. And of course, the sum of all these relative frequencies will equal exactly 1 unless you've double counted or left out a piece of data. Also, sometimes we'll ask for a cumulative frequency or a cumulative relative frequency. Cumulative just means the relative standing, or in other words, how many pieces of data have hit this or less. It's like a less than or equal to. So for example, when you take a standardized test, they'll give you, oh, your percentile was 90 whatever percentile. That's your cumulative standing. That tells you you beat 90 whatever percent of the test takers. Okay, so that's cumulative relative frequency. Okay, and again, those are usually going to just be percentiles. Okay, you can give them as a ratio, but again, not particularly, sorry. Typically, they're given as a percentile. All right, so my data on the QWERTY keyboard, my minimum value was 0. My maximum value was 14. We have 52 pieces of data, which is relatively small number of data. So we're going to shoot for 5, 6, 7 classes, somewhere in that range, which means if I have a class width of 3, I'm going to be hitting around 5 classes. So that's what I did. Now, you might say, why'd you start with -1? Well, I actually originally started with 0, but then when I went on Desmos insisted on making the lowest value -1. And that's because typically it's nice to have a value below your lowest number when you graph so that you can kind of see the whole picture, right? You don't like to start your graph right on the very first value because then it's like jammed right against the edge of your graph. So I started with -1, even though scores, of course, can't be negative. But anyway, start with -1, have a class width of 3, so -1 to +1. There were 5 words that scored in that class. That's my frequency. To make it a relative frequency, I would take 5 divided by 52 because there were 52 words total. And there it is as a percentage. Okay, here's my cumulative frequency. There are 5 words that scored 1 or lower. Here's my relative cumulative frequency. Again, 5 divided by 52. Again, you can make that a percentage if you want. I purposefully did 1 as a percentage and 1 as a ratio just so you can see either way. Okay, my next class, words that scored 2, 3, or 4. There were 22 words that scored a 2, 3, or a 4. So that's 42.3%. Now notice cumulative. I'm now saying how many words scored 4 or lower? Well, there's 27 such words because there's 22 in this class plus 5 that scored below that class. So 27 would be my cumulative frequency, 4 or less. And of course, my relative cumulative frequency, 27 out of 52. Okay, and as I continue, word scores of 5, 6, or 7, there were 19 of those. There's the percentage. Cumulative frequency, well, 46 of the words scored 7 or below, right? 19 here, 22 there, 5 there. 46 of the words scored 7 or below. Relative cumulative, 46 out of 52. Okay, words that scored 8 to 10, so 8, 9, or 10. There were 5 there. Again, percentage. I'm now cumulatively up to 51 out of my 52, right? I'm almost there. None scored 11, 12, or 13, and there's my last one, scored 14. And so there's all my data. So I've created 6 classes, and each class has the same width. So this is an appropriate table to organize that data set with. Now, here's the same preamble scored on the Dvorak keyboard. Notice here I did actually start with classes of 0 because I did not take the time to make these graphs in Desmos. You'll see there's really no reason to make 2 of every graph. Once you know how to make one of the graphs, you can just repeat that. So anyway, here it is on Dvorak, and you could see the highest score on the Dvorak was less than or equal to 5. So if you buy into their word scoring system, you would say the Dvorak keyboard must be faster. By the way, you actually can go out and buy a Dvorak keyboard if you're really interested and you think this is a great idea. You can go online and purchase a Dvorak keyboard and learn a whole new keyboard layout. Okay, here's just a quick note. The classes, they don't necessarily have to say 0 to 2 and 3 to 5 and so on. You can just use class numbers or some other type of labeling like freshman, sophomore, junior, senior, right? So these don't have to be numbers. They could be any other type of labeling. Those are classes as well. Oops, sorry. Okay. Some notes. When you set up classes and you have numerical classes, you'll be creating what are called class boundaries. So a class boundary is where does one class end and the next class begin? So if we go back to our QWERTY example, our first class ends at 1 and our next class begins at 2. But where's the boundary? So in other words, when I make a histogram, in a histogram, my bars must touch. I can't end one bar at 1 and then have a gap and start the next bar at 2. So on a histogram, I make one bar go to 1.5 and then the next bar starts at 1.5. You see, your midpoint between the end of this class and the beginning of this class, that's your class boundary. So your next class boundary would be at 4.5, 7.5, 10.5, 13.5, and so on. So those are your class boundaries. That's where you're actually going to be drawing your line when you make your bars on your histogram. Okay. You might be asked about class midpoints. That's pretty self-explanatory. That's the middle of each class, or in other words, the middle of each bar after you've drawn your histogram. And you might be asked, well, what's the class width? In this case, we set our class width to be 3. If we had set our class width to be 1, we would have had too many classes, right? We'd have too many bars in our graph. So we chose a class width of 3, so we would have 5 or 6 classes. All right, so all that out of the way, let's start making some graphs. And again, we're only going to graph the QWERTY keyboard. You could, if you wanted to, go ahead and score the words on the Dvorak and make your same graphs again for more practice. Knock yourself out. But I'm only going to do QWERTY. So these are our main 8 graphs. The frequency histogram, the relative frequency histogram, the frequency polygon, the relative frequency polygon. Okay, those 4 are all basically showing the same distribution and read the same way. Okay, then we have the cumulative graphs, the bottom 4. We'll make a cumulative frequency histogram, a relative cumulative frequency histogram, a cumulative frequency polygon, and a relative cumulative frequency polygon. That's a real mouthful, so rather than saying all that, we just say ogive. So when you see this word ogive, it means make a relative cumulative frequency polygon. So let's start. We're going to start with a frequency histogram. Okay, so we simply go, let me go back to our data table. So we're basically going to be making a bar, again, using our class boundaries. So we're going to go from negative 1.5 to positive 1.5, and we're going to make a bar with a height of 5. Then from 1.5 to 4.5, we're going to make a bar with a height of 22. And we're just going to continue doing that, okay? So here we are. From negative 1.5 to positive 1.5, we make a bar with a height of 5. From 1.5 to 4.5, we make a bar with a height of 22. And we continue doing that, and we've created a frequency histogram. Pretty simple. Now, it's very important on your frequency histogram and on all graphs that you label both your axes. Okay, so down here, we're talking about the word scores, and over here we're saying the frequency, how many of these scores landed in each class. And there you go. Oh, also, make sure you have a title. So when you take the AP exam, and this is very common, students tend to forget a title, they tend to forget to label both their X and Y axes, and they lose a lot of points on very simple mistakes. So make sure you always give a title and label your axes. Okay. Now, notice my bars touch. The reason they touch is because this is a histogram. You'll see a gap here and you say, wait a minute, Mr. Crow, bars aren't touching here. Well, that's because that class had 0 values in it. So that's why that bar and that bar don't touch. We're showing the reader, no data was over here. Okay. By the way, a lot of students use the word histogram as a synonym for bar graph. They are not the same. A bar graph is used when I have categorical data, okay, data that is non-numeric. Okay, so in other words, if I said, what's your favorite color? And I kept track of the results, a bar graph would be appropriate for that data because color is not numerical. Or if I said, what's your favorite animal? That would again be a bar graph. The bars do not touch in a bar graph because down here I have categories that I could put in any arbitrary order: dog, cat, unicorn, dragon, whatever. Okay. Whereas when I have scores, they go in order. And that's why you make a histogram and your bars touch. So that's the difference between a histogram and a bar graph. Okay, next graph. Oops, this is a little out of order. Well, I guess I have two graphs in one here. Oh no, here it is, sorry. Next graph, the relative frequency histogram. You'll notice that this graph looks identical to the regular frequency histogram. The only difference is your vertical scale. Instead of being the raw count or the raw frequency, it's now a relative frequency. So these are proportions, ratios. Actually, oftentimes these are going to be written in percentage form. So you'd say, oh, okay, this is, looks like almost 10%, 9.6 to be exact, right? This is just over 40%. 42.3 to be exact, and so on. So relative frequency just means your vertical scale is changed, but notice the shape of the graph looks identical, okay? See, same shape, you've just changed your vertical scale. And of course, that's an easy mistake to make on your test or on the AP exam when you're asked to make a relative frequency histogram to accidentally make a regular frequency histogram, or vice versa. So just make sure you read the words carefully and pick out things like relative and make sure you get your vertical scale to match. Okay, next, frequency polygon. I left my histogram in the background just to show you how the frequency polygon compares to the histogram, the frequency histogram. Now there's more than one correct way to make the frequency polygon. I used the class midpoints. So for each class midpoint, I said there were 5 words in my first class. So at the midpoint of my first class, I put a point. The midpoint of my second class, there were 22 words in that class, I put a point. There's the midpoint of my next class, midpoint, 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 so on. And then I connected each midpoint with a straight line. That is an acceptable way to make a frequency polygon. It's also very common, and I believe our book does this method. Instead of using the class midpoints, they use the left edge or class boundary. So just take each one of these and shift them over, right, to the beginning of each class, and then line those up, draw in your lines. You'll see you would actually have the exact same shape. It would just shift everything over by, in this case, 1.5 units. But the goal of these graphs is to show the distribution visually. So it really doesn't matter if you're hitting the class midpoint or the left end of your class boundary. It's going to show the exact same shape, or in other words, the same distribution. And you can see how the frequency polygon versus the histogram, again, they're showing the same basic shape. So they're pretty much interchangeable, but again, follow directions when you make these, okay? Oh, let me back up. On the labeling here, for some reason, some students really have trouble with these class boundaries. It just boggles their mind. Class boundary is 1.5, but I don't have any data that's 1.5. Well, that's intentional. If you had data that's 1.5, which bar would I put it in? Right? I can't have my class boundary landing on an actual value in the data set. And that's why I set up my classes, and then my class boundary is always in between. So anyway, if that is too difficult for you, rather than drawing it this way, you could write your class boundaries down below here. So for example, this class here is 2 to 4, and then this class here is 5 to 7, right? So instead of labeling like this, you could label this way. But realize, even if once you label this way, what's this point right here? It's still 4.5, right? So just an aside. Okay. Now, the relative frequency polygon, guess what? Looks just like the regular frequency polygon. The only difference is your vertical scale, right? Instead of being the raw frequencies, it's now relative frequency. And so these are ratios, or you could again put them as percentages. Okay. So there you go. If you can make one, it's very simple to make the other. Okay, so those are our 4 frequency style graphs. Next, let's look at our cumulative style graphs. Okay, so here's our cumulative frequency histogram. Cumulative frequency, remember, okay, that is a less than or equal to. So these numbers are always staying the same or increasing. Can never go down because we're saying this amount or less. So they never go down. So your cumulative frequency graphs are always trending up, whereas your regular frequency graphs, they can go up, they can go down, they can bounce all over the place. So you read these graphs differently. Actually, let's talk about how you read a graph real quick. So when I'm reading this particular frequency graph, I'm looking at its overall shape. And I see the overall shape is high in the middle, low on both ends. So it's fairly balanced. It's fairly symmetrical. And if you know from previous math classes, you might know the word normal. This is fairly normal distributed. Okay. Now, realize this cumulative graph is showing the same data set, but it looks entirely different. Okay. So the way you read a cumulative graph, you're not reading the height of the tails. You're reading the change from one class to the next, the change from one bar to the next. So you can see the change in the beginning is quite steep, meaning there's a lot of increase in data in this region, and then it's very slow, meaning there's not a lot of data in this region. Okay. A lot of data in this region, not a lot on the tails. It's showing the same thing, it's just read differently. Okay. So remember, you read cumulative graphs based on the rate of change from one bar or one class to the next. Okay, you're not reading based on the raw height. Okay, so that's how you make a cumulative frequency histogram. Notice you top off here at 52 because we had 52 words. If you wanted to, you could keep going and keep drawing a horizontal line at 52 forever. Oh, and again, make sure you're labeling your axes. All right, here's your relative cumulative frequency histogram. Only difference here is now your vertical axis is no longer on a scale of 52. I didn't write my scale over there, but I could just bring this over and say there's 100%, right? And then halfway, that would be 50%, so on and so forth. Okay, so it's just a different vertical scale. Instead of raw number of data in each class, it's now ratio or percent in each, or less than or equal to, I should say, for each class. Okay, here's our cumulative frequency polygon. Again, I use midpoints of my classes to make this. You could use left endpoints of the class if you prefer. And it's made just like our other frequency polygon. The only difference is it's cumulative. So again, once we get to 52, we've got all of our data. Okay, and one more graph to go. The ogive, or relative cumulative frequency polygon. Okay, the ogive is going to look just like your cumulative frequency polygon, except your vertical scale, instead of being raw number or raw frequency, your vertical scale is now ratio or percentage. So once you hit 1, that means you've captured 100% of the data. So 100% of our data have scored this or lower, whatever that number is. What is that, 17? It's actually, right here you can see it's actually at at 14 was our highest scoring word. Okay, so those are our main 8 graphs. They're not that hard to make. The difficult thing is to choose the right class widths and make sure you hit your class boundaries correctly. And what I normally find students mess up would be just knowing the vocabulary. So when the test question says make an ogive, and by the way, this is pronounced ogive, like O and then jive. That's how it's pronounced, but it's spelled with a G. Pronounced ogive, spelled with a G. So on the test, when I say make an ogive of whatever data set I gave you, are you going to know which of these 8 graphs to make? That's where students make mistakes. It's just learning the vocabulary and being able to associate that vocabulary with the correct graph or the correct calculation as we move forward in the class. So highly recommend read your books. It will help you learn the vocabulary. If you're still having trouble, make flashcards, watch additional videos, go to websites and do additional practice. So learn that vocabulary. That's a must, because to be honest with you, these graphs aren't that hard to make. All right, now, as I mentioned earlier, the whole point of these graphs is so we can visually see the distribution. Here's our definition of the word distribution, right? How often does the variable take on different values in the data set? Now, once we make our graph, we like to talk about that shape. What do we see? And these are the 3 main choices. There's some other choices. We'll get to those later, but for now, these are the 3 I want you to know. Is the distribution symmetric? Something like this right here. That's symmetric. And I'll even be more specific. Hopefully you know that term. That's the normal distribution. It's perfectly symmetrical. It has a peak in the middle above the mean and median, and the tails are both low, and it's symmetrical about the mean and median. That's the normal distribution. But notice normal, that's not the word we're going to use for all symmetric, right? We could have something that looks like a U. If my distribution looked like a U, that would be symmetric. Wouldn't it be normal? I could have a distribution that's bimodal, right? So looks like 2 humps, like something like that, right? That's symmetric. It's not normal. So please don't use the word normal and the word symmetric as synonyms. Normal is one specific type of symmetric distribution, but there are many, many symmetric distributions out there. So don't interchange those words. Only say normal when you have normal. When you have something else that's symmetrical, say symmetric. And we'll learn some other typical types of symmetric graphs in future lessons, like bimodal, uniform, etc. Okay, now if you don't have something that's symmetric, then you have either a skewed right or skewed left distribution. Okay, so this guy right here, this is skewed right. Okay, and the way to read right or left is the tail. And the reason we call this skewed right is because this tail on the right will pull the mean to the right of the median. Okay, this one over here is skewed left. We call it skewed left because the tail is on the left, and that tail will pull the mean to the left of the median. Okay, in other words, the mean on this will be lower than the median on this data set. And over here, the mean will be greater than the median on this data set. Okay, it's easiest to read the shape from a frequency graph or a relative frequency graph. It's harder to read the shape from a cumulative graph, right? Because remember, here's a cumulative graph. If I try to read the shape of this, I have to say, going up quickly through here, not so fast in the beginning, not so fast at the end, right? It's hard for me to look at this and say this is symmetrical, approximately normal. So I would highly recommend, if you have to talk about the shape, make a non-cumulative graph to talk about the shape. It's difficult to read this and get the shape correct. All right, so that's our main shapes. Okay, there are a few more graphs. I already mentioned bar graphs, so make sure you use a bar graph when you have categorical data and the bars do not touch in a bar graph because the order that you put those categories is completely arbitrary. Okay, how do I make a dot plot? Well, a dot plot is actually very much like a bar graph. So put yourself back in, say, preschool. Might be the first graph you ever made, a dot plot. Your preschool teacher might have given each child a sticker when they walked in the door and said, "Kids, don't put the stickers on each other." And then the teacher would say, "Okay, I have pictures of different animals on the board. I want you to come up here and put your sticker above your favorite animal." Right? And then all the kids would go up to the board and start putting their stickers. And the idea would be to make a nice vertical column of stickers, but preschoolers are probably going to make a mess of it. But anyway, you would end up with things like, dog, cat, dragon, unicorn, so on and so forth, right? And then kids would come up and put their stickers, and based on the number of stickers, you would know that's how many students in the class chose each animal. So a dot plot is basically just a bar graph where each dot represents a piece of data in that category. So they're pretty interchangeable, dot plot versus bar graph. Okay, and there is a dot plot for the QWERTY word scores that we made earlier. So you can see 1 word scored 0, 4 words scored 1, so on and so forth. Okay, so that's a dot plot. All right, another important graph you should know how to make is a circle graph, or also sometimes referred to as a pie chart. Okay, realize a circle has 360 degrees. So you have to divide this thing up, right? Start by drawing a radius. It doesn't really matter where, any old radius will do. And then figure out how many degrees each class represents. So in other words, multiply your relative frequency for each class by 360 degrees. That tells you how many degrees to assign to each class, right? So if my relative frequency for a particular class is a quarter, right? I would do a quarter times 360 and say, okay, I need 90 degrees. And then I would make that 90 degrees, and I'd make some kind of color and a key over here to read it. So I made one for our QWERTY word scores. Not the best color scheme, but that's what PowerPoint did for me. If you're making it by hand, try to use colors that are not so similar, right? It's really hard to read this key and figure out, since they're like almost all blue, it's hard to figure out which one is which. So when you make this by hand on a test, use blue, use red, use green, use colors that are not all blue. And of course, when you print these things in black and white, it can be even more difficult, just shades of gray. But anyway, that's how you make a pie graph, pie chart, circle chart. Oops. Okay. Next, stem plot, or sometimes called a stem and leaf plot. To do a stem plot, it's actually an excellent way to organize your data in ascending order. So when you make your stem plot, you're going to organize your data in ascending order. And I made a stem plot for our QWERTY word scores. And this is a special type of stem plot called a split stem. Since our word scores were almost all single digits, if I don't use a split stem, I would just have one row with all my single digit scores, and then one row with my 3 values that were 2 digit, which isn't enough because we need 5 or more rows. These are like my classes. So what I did is a split stem, meaning my first row, I went values of 0 and 1. My second row, I went values of 2 and 3. My third row, 4 and 5, and so on. So each one of these rows has a class width of 2. So I split every 10 values up into 5 rows or classes. Okay, and that allows me to have classes that are all the same width, and have enough classes that I can actually see kind of a distribution here. You basically read a stem plot the same way you would read a histogram or a dot plot. I can turn it like this, and based on the heights of each one of those, I can kind of see, well, not kind of see, I can exactly see how many pieces of data landed in each class. Okay, so the stem plot is another way of showing a visual representation of the distribution, and at the same time, it's showing you the actual data in ascending order. So it's pretty nice. And the way you read it, by the way, I should have a key. Make sure you always have a key. I would say that 0-4 equals the number 4. Okay. So when you make a stem plot, the stem could be any number of digits. It doesn't have to be a single digit for the stem. The leaf, however, must, let me say that again, the leaf must be 1 digit. So if you have numbers that are very large numbers, you can have a large stem over here, and then your leaf is again 1 digit. So let me make up some data. Let's say I have, I don't know, people's weights. So say I have things like 120, 121, 121, 123, right? So on and so forth. And, you know, maybe I go up to, I don't know, 192. Okay. So here, my stems, I could now make 12, 13, 14, 15, 16, 17, 18, 19. So my stems are now 2 digits long. And then I would have a 0, 1, 1, 3, so on and so forth. And then when I made my key, and this is why you need a key, right? A stem of 12 and then a leaf of 0. Does that mean 12.0? Does it mean 1.2 million, right? In this case, it means 12-0 means 120. So that's why you must always include a key when you make your stem and leaf plot, because the key tells the reader how to place the decimal point on your data. Okay. And again, each leaf, let me say that one more time, each leaf represents a new piece of data. So every time you put a comma, new piece of data. Each leaf must be 1 and only 1 digit long. So if you have a really large number of values with many decimal places, etc., oftentimes you'll round those off. So if you're talking in the millions or billions, you'll round those off to the nearest million maybe, or the nearest 100,000, or the nearest what trillion or billion, whatever it is. Same thing with decimals, with many decimal places. You might have to round them off to the nearest 100th or the nearest 1,000th or whatever. So you will do some rounding. And also very important, you can do split stems, right? You can have 12, 12, 12. You can have more than one 12 going on here, but you can't skip. You can't go 12, 14, 15, 16, 20, because that is, when you go to graph it and look at it this way, you're skipping values, and that makes things not look correctly. Okay, so you can never skip a stem. You must go in order. So even if you're doing a split stem, if I split 12 up into 2, right? So I would do like 0 to 4 here, and then 5 through 9 here. I would have to do 12, 12. Then from that point on, I got to do 13, 13, 14, 14, 15, 15, so on and so forth. So once I start my stem labels, I can't skip. So make sure, again, choose an appropriate way to round so that you have the right number of classes or rows showing up in your table. Again, 5 to 20, and don't skip. So if you're having to skip, then you needed to round off differently. All right, so that's a stem plot. And last graph for today is the time plot. the time plot shows changes over time. Very common use of a time plot. People who follow the stock market, whether it's the whole market, individual stocks, etc. So this particular time plot is showing the price of Tesla stock over time. And so you read this showing, oh, look, in the beginning, stock was going up, then it kind of went down for a bit, and so on and so forth. It stayed fairly flat, and then right in here, oh, wow, it took off. So as an investor, hopefully you bought a lot of Tesla stock before this point right here, and you gained a lot of value, a lot of money. But you just basically track change over time. That's what a time plot does. Okay, hopefully that all makes sense. What we're going to be doing moving forward is, again, this would typically be your homework assignment. You would watch this video at home, and then you would come to class online at this point in time, and we would go over any questions from the video, and then we would do the homework problems and go over questions on the homework problems together. This being the first day, you are unaware, so that's why you're watching this video in your class time. And of course, this has been a little over 50 minutes, so when we finish up watching this, you can ask me questions during class for this first lesson. And I will post all of these videos on YouTube, so that way if you're ever absent, or if you want to go back and re-watch a video, you're welcome to do so because they'll be posted on YouTube.